It looks like we can get going. Welcome back, everyone. So it's our final class meeting aside from the final exam that's coming up. And that means we're basically done with the class. We're just reviewing some topics to get us familiar what was going to happen on the real final exam. Any questions, folks, at all before we get started? Okay, let's maybe run through just a couple announcements. We're going to be working on these documents here, mainly because I wanted to leave everything down below really just up to you and your own personal studying. All of these are blank exams. You could print them out, treat them like a real worksheet, but the more you treat them like a real final exam while you're studying, the more effective they're going to be by far. So down below is just some guidance on great ways to study for a final exam. And the solutions to the final exam are all in this file here. If anything looks missing or just incomplete or just flat out wrong, just let me know right away. I'll check it out and make any corrections as necessary. But you can open up that file there to find the solutions. And so what we'll do is this exam right here, this one was also another final exam that was given. I forget the year here, but I think it was a little bit more recent. Well, any questions at all, folks, before we dive into 6-7 and then the document below? Okay, so let's take a look at our section 6.7. This was the last official problem for the course. I think this one was a little bit tougher, but it's a good one to review on since lots of stuff happens here on this problem. It says at the start of an experiment, we have 10,000 bacteria present. From that information, just because they said at the start, this quantity right here is going to be an initial value. So let's write out A is 10,000. Next, it says after 10 hours, we have 35,000 bacteria that are found, and we're assuming the population is growing exponentially. I'll pause on this piece of information here. Let's highlight it. And let's first talk or write something out for the exponential growth of the model. If it's growing exponentially, we typically in this course write it out as A for an amount, or you could say P for a population or anything along those lines. I'll go with A. So A at T is going to be equal to initial amount, 10,000, times e to the power of R times T. Part A is asking us to determine the growth rate R, but we actually need the whole entire model written out before we can get to that step. So our goal is go for that R right here. And this is where the information in gray comes into play. It says after 10,000, or excuse me, after 10 hours, we have 35,000 bacteria present. So the amount at 10 hours equals 35,000. I always thought those problems are weird because who's counting 35,000 different bacteria? But there's an actual way they do this. They put like a slide under something that emits light, and every time a photon of light is blocked, they assume that it was a bacteria that blocked it. So there's an actual systematic way of really counting these things if you're curious. So at 10 hours, we have 35,000. And what this does for us is we're going to plug 10 right inside here in the model. It'll give us a brand new equation for which R can now be solved. So that second piece of information is what's allowing us to get through the problem. Let's write this out as 10,000. Then e to the power of R times 10. So that's where the 10 gets thrown in, is now equal to 35,000. First thing we want to do is divide 10,000 into both sides of the equation. We will get e to the power of 10 times R, or R times 10 if you prefer, is 3.5. It's kind of a nice problem to just run through that. Next, if you take the natural log of both sides, here the base exponential goes away. You will get 10 times R equals the natural log of 3.5. So we're just one step away. When it said determine the growth rate R, here we go, just divide by 10, and R is equal to natural log of 3.5 tenths. Where the instructions say do not round, that means we're just going to leave it like this, use it in the next portions, and only round our final answers. Any questions at all, folks, on that output there? Okay, so that's one down. Next, it asks us, how many bacteria were present 3 hours after the start of the experiment? We'll round to the nearest bacteria, and same kind of information. We're not trying to round the intermediate computations, only the final answer, just to try to get as most of an accurate value as possible. So amount of bacteria at 3 hours would just be A of 3. That means we're plugging 3 right here, but we also found the value of R, so we can plug it in there as well, all at the same time. So now it's turning into the initial amount, 10,000. Then e to the power, this is a strange looking power, but here it is, natural log of 3.5 divided by 10. And that whole quantity has to be multiplied by 3, still in the exponent position. So all of that now goes into the calculator. This is most of the credit on a real exam as far as partial credit goes for grading. We just have to get an actual figure. So importing that into the calculator, just for extra help on that one, let's do what we did before in other classes. It would look like this in your calculator as you type it in. 10,000 e to a power natural log 3.5. Be sure to close that parenthesis right there. Then divide by 10 times 3. This does not turn into an order of operations problem like this. The 3 will multiply into the numerator as intended. Then close that parenthesis. And we should get the right value with something about like that. Let me try it in this calculator here. And let me know as usual if you're getting something different. We'll try to reverse engineer it and get the right value. So 10,000 e to a power natural log 3.5 tenths times 3. We're getting all together to the nearest bacteria, 14,562. 14,562